welcome. In this lecture, we are going to talk about various levels of digitization in single loop feedback control in switch mode power converter. So, in this lecture, we are going to talk about, we want to recapitulate our analog voltage mode control, which is a single loop control. Then we will talk about how to digitize the single feedback loop. Then what are the sampling and quantization with some waveform, and then we also want to discuss sampling delay and timing diagram. And finally, we want to summarize single loop digital voltage control, what is the overall architecture. So, if we talk about analog voltage mode control, which we have discussed extensively in our previous lecture, I think lecture number 6. Here we are talking about a voltage mode control. In this voltage mode control, we have this outer voltage loop, because this is the output voltage, then it is compared to the reference voltage, the error voltage goes to the compensator. So, this is our compensator, and then this is our compensator. Then output of the compensator actually is compared to the sawtooth waveform, and that comparator output goes to a latch circuit that we have discussed. Okay. And then there is a dead time, that as well as the gate drive, so which will generate the respective duty ratio. Now, in this control, we have discussed that it is under trailing edge modulation, where we will have a switching frequency clock. This is a clock, and if it will turn on at every switching frequency clock. Okay. So, this will be the switching frequency clock edge. So, this is our FSW, and it will turn on at every switching rising edge of the switching clock, and this technique is called trailing edge modulation, and that we have discussed, trailing edge PWM. If we want to close the output voltage loop, then first thing again the first thing is required, we need to digitize this voltage signal. That means, this is the output voltage. Again, we may not use a straight ADC, we may have to use a resistive divider or op-amp buffer circuit. But anyway, in general, if we consider the basic block, we need an analog to digital converter, and this will generate the sample as well as the quantized output voltage, and this output voltage will be compared to the reference. So, it may look from here onward you will have digital blocks, because from output of the ADC is the digital. So, the reference has to be digital, okay, because we need to match the domain. We cannot have any digital signal compared to the analog. So, all should be taken into digital, or all signal can be kept into analog. So, here we are talking about the digital signal. Now, this ADC means what? The basic two things. In ADC, we have a sample and sampler, as well as sample and hold will be there, because ADC will also have register. So, it will also hold, and also it will have finite resolution, because every ADC, whether it is a 8 bit, 10 bit, 12 bit. So, depending upon the bit size, the resolution of this staircase will actually change. So, higher resolution, this staircase will slowly become like a straight line. So, that the size of this step will be reduced if you increase the bit size. But if you use a higher bit ADC, naturally this large data has to be processed through a digital system, and as we increase the bit size, let us say in our computer we talk about 64 bit machine, 32 bit machine. So, suppose if you have a 8 bit data and if you have a 12 bit data, naturally for 12 bit data, for the same clock rate, your hardware resource will increase and the power consumption will also increase. So, in order to limit the power consumption, because we are all talking about high frequency power converter, where the whole thing can be a single IC, each and every power actually matters. So, we cannot use arbitrarily large bit size, so we have to be very careful. Okay. And you will also see that this staircase will also have a quantization effect, and in the subsequent lecture we will show, even in hardware, that there is a certain requirement of this quantization as well as the ADC quantization, otherwise you will end up with limit cycle oscillation. So, here this A to D converter has a sampler, and it will also have a hold because of the resistor, and it will also have a quantizer. But every ADC will have some conversion time, and that is represented by the delay. And this conversion time, actually if we want to draw this timing diagram, that means this is the digitized voltage, that means this is the digitized voltage, digitized output voltage. So, that means it will be a number. So, if it is an 8 bit ADC, then it will be 8 bit number, and so on. So, this is the continuous time analog output voltage, which is a time domain waveform, and suppose we have sent a signal, because ADC require a clock, that means that what clock edge you want to sample. Suppose you have sent this is a sampling command, this is let us say our sampling clock. Suppose you have sent that I need a sample here, but because of the conversion time this data will be available after certain time. So, this duration, that means your data is available as if here, and this is a comment. So, this is your conversion time of the ADC. Okay, but this conversion time what we are showing in this waveform looks like very small, but this conversion time can be very large, because if you are talking about low power application and for let us say just a point of load converter and you are using an ADC. So, if you want to reduce this timing conversion time, that means your ADC should support high sampling rate, that means you need to have a very powerful ADC and that will consume lot of power, and also the cost will be very high. But suppose even if you use a high sampling rate ADC, but if you sample at a lower rate, you can reduce the power consumption. So, if you sample at a lower rate, naturally the conversion time will increase, and this depends on the type of ADC. Suppose if you are talking about the pipeline ADC, that pipeline ADC delay will depend on the number of pipeline stages and the clock at which you are sampling. So, all this will be discussed when we will talk to A to D and D to A converter. But here we should remember this conversion time can be much larger than switching cycle if you use a low power A to D converter. But with this such large delay, how to handle the switching converter performance, how to handle different type of stability, that we will also discuss in this course. But here I want to give a very basic introduction, that means there is a delay and this delay will cause the availability of the actual data which is much later than when you send the actual sample signal. So, now again the next part, when you have a digital signal here, naturally this compensator has to be discrete time. That means this compensator will be sitting at the digital control platform, which can be microcontroller, ASIC, FPGA, whatever. So, in this course we will be prototyping using FPGA. So, as if this compensator will be sitting in the FPGA, and this FPGA means there will be registers and some arithmetic, and that means it is a ALU operation, arithmetic and logical operation, and there will be some memory block. So, all this compensator computation will happen by this ALU block. Okay. And we want to design some of this block, that means a different compensator using Verilog HDL in this course. So, next the RAM, since we are all talking about digital, because so far all these signals are digital. Okay. So, these are digital. So, naturally this RAM should be digital. And how do you generate this RAM? This RAM, a very easiest way, you should use a counter, as if the counter is just kind of incrementing, right. So, the counter is keep on incrementing, again you reset the counter. But the question is, if you compare an analog RAM like which is a smooth, okay, and it is just, so this analog RAM has no resolution problem, but here you have a resolution problem. And if you want to reduce the step size in order to closely approximate to an analog RAM, then the bit size of this counter, that means the counter bit we should increase the counter bit, at the same time we should increment using a high frequency clock, and that will also lead to lot of power consumption, and it may not be possible to achieve high resolution for high frequency, because the clock requirement can be impractically large, and we will discuss different architecture how to handle. So, in summary, that means if you use just a counter, it can be a modulo counter or it can be a free running counter. In case of free running counter, you have to compare with the upper limit, and we can suitably adjust the switching frequency just by changing the upper limit if we keep the sampling clock same. Here we are resetting the counter by comparing with the upper value, and this reset pulse can be used, that means when it equal we can use that as a switching clock, because we need to synchronize with this switching clock, right. So, this will be a switching clock. So, this synchronization can be done if we just compare with like a 0 block, that means if we put an equality block 0, that will be like your switching frequency clock. Okay. So, this part we will also discuss when we want to implement using the digital circuit, how to implement this this architecture DPWM. And this is the maybe a zoom version of this counter based sawtooth waveform, where you can see the counter is simply incrementing, and the time period of this clock, which is a high frequency digital clock, is T clock, okay, and the switching frequency is 1 by Fs. So, if you want to decrease this resolution, that means if you want to improve this resolution, then naturally the time period T clock duration should be reduced. As a result, you need a high frequency clock, that is a digital clock. And we will discuss that when you talk about DPWM architecture. There are various architecture in order to make it practically feasible for high frequency application. But the bottom line is this: because of this quantization in the RAM, it may pose a limit on your duty ratio, because if you compare this with your controller output, unlike in a continuous waveform where you can perfectly intersect, here there can be mismatch between the actual comparison, and that may lead to some duty ratio resolution problem. So, you have to be very careful about the selection of the resolution. So, this is the overall architecture of the DPWM block, digital pulse width modulator. It is a voltage mode control, and if we show the waveform, overall waveform, here it is the FSW clock, which is a switching clock. And again we want to recall, which we have discussed, I think lecture number 7, yes, modulation technique. This voltage mode control in analog control is a trailing edge modulation, and if you consider this almost equivalent to analog RAM, you see whenever this switching clock comes and this time the switch is turned on and the current is rising, right, and the sawtooth is rising, and this sawtooth reset again at the next rising of the switching clock. So, that means this sawtooth waveform is sync with the switching clock, and that actually matches. That means, when the rising edge come, sawtooth start incrementing, when the another rising edge comes, sawtooth is reset and again start. And the current waveform and the converter turn on is also sync with the clock, because it is under trailing edge modulation. But if you look at the switching frequency sampling clock, which is this sampling clock FVS, which is shown here, as I said, there has to be a finite time which will accommodate the conversion time of the A to D converter as well as the controller computation, because it will also take some time to compute, because you are using a digital platform. Because you want the sample to be here and this data should be available here. So, this is the delay. Okay, so, that means once you send the sampling signal here, then there will be ADC conversion time and the controller computation time, and your data will be ready here. So, you can see the data, which is a red line, and this data VC, which is nothing but the output of the compensator. So, this data is getting updated with the switching frequency clock, but the sample is captured at the sampling clock. So, that means there is a difference in the time delay, and that is to accommodate the conversion time. And then here we are talking about just one sample per cycle, and that will be updated, and then accordingly then rest of this waveform look like a similar to voltage mode control. In fact, in digital control, if you take one sample per cycle, you do not need a separate latch, because since you are taking only one sample, it is insensitive to any noise, because it is not updating. So, we can eliminate this latch circuit, because latch is already taken care, because the DPWM itself has a delay. Okay, what latch used to be there. So, DPWM takes the sample and this is hold for the rest of the interval. Here the delay can be even larger than the time period, and that we will discuss when you go for high frequency implementation. Now, this finite effect of finite quantization, that means if your quantization level is not, because if you take the digital controller loop, this is our power converter, here we will have a driver circuit and this is a sensing signal. So, all these blocks are analog, these are analog, because it is a real converter. Okay. Then this is our A to D converter, where it will be a sampling followed by quantization, and these blocks are basically digital, the whole blocks in fact will start from here. So, this is the digital block. Okay. So, that means if we so this block I would say from here to here, this is our digital and these blocks are analog. Okay. So, here there are two places where you need to consider quantization. One is the ADC resolution, where the quantization will come into picture. Another, we are using a counter base or maybe other architecture of DPWM, where it will be a staircase. So, the resolution of this staircase, what is the clock frequency, all these things, that will also insert a quantization. So, these two quantizers are there, and we will show you when you go to design, there is a specific requirement of the quantization selection, otherwise it will end up with limit cycle oscillation. And this quantizer, if you compare with a continuous time RAM, that means analog RAM, this quantizer actually, if you take the output, controller output or any signal, if it is analog, then wherever it intersect, that will be your duty ratio. But because of digital, you have to wait for the next turn. So, this can insert a mismatch with the continuous time version and the digital version, and that will actually create a duty ratio resolution. Okay. Next, if the duty ratio resolution is poor, DPWM, that means the resolution of this block is poor than the DPWM of the ADC, and we will discuss in detail, then this quantized voltage level may not be inside the zero error bin. That means, it may not be constant between two successive staircase, and exact duty ratio may not be achievable, and this may eventually go outside the zero error bin, and it may lead to some kind of instability. So, sometime we may call it a limit cycle, or it may be a high periodic behavior. So, that means, this finite DPWM resolution can end up or lead to finite resolution problem, or which may eventually go to either limit cycle or high periodic behavior. So, in summary, we have discussed that we have actually recapitulate analog voltage mode control. Then we have discussed how to digitize the single feedback loop. Okay, then what are the like ADC, DAC, sampling rate, quantization, some basic idea how to digitize the single feedback loop. Then we have considered sampling and quantization, but only basic, we will discuss in detail. Then we have also shown that there will be sampling delay, and we have also drawn some timing diagram that will motivate that when you go to more practical design, such delay we have to consider, and with this delay we have to extract how much performance can be achieved. Okay, and what will be the fast scale stability. And finally, we have summarized what are the basic step of digital control, digital voltage mode single loop control. Okay, so we want to stop here. Thank you very much.